In this video, I will run you through and compare the three different fields that you will cover in your A2 syllabus, namely gravitation, electric, and I will not really touch on magnetic fields yet until the magnetic topics have been covered in our videos, right? So we're going to zoom in into gravitation and electric, but I just want to let you observe the field lines across these three phenomena. So when we talk about fields, right, we're talking about a region of space that if there are certain properties that you fulfill, you will experience a force. For example, gravitational field would be a region of space where a mass experiences an attractive force, and electric field is a region of space where charge will experience an attractive or repulsive force. So these two pretty similar. If you look at this drawing, right, it looks a bit like never see before, right? Okay, so this one, we'll talk about it later in chapter 22 and chapter 23, but I just want you to remember that magnetic field is pretty unique. And the idea about field, right, is that you don't have to be touching to have that force exert on something else. It is known as a non-contact force. All right, so now we're going to zoom in and stare at the field lines and compare the gravitation and the electric field lines. What kind of similarities do you see and what kind of differences do you see? What do you think? You can pause the video and write some observation. All right, so the first thing you'll notice is that the shape is pretty similar. We call this a radial field because it looks like it is directed towards the center. It's along the radius. So we call this a radial field. This one looks like it's along the radius. Okay? And because it's along the radius, we know that this must be perpendicular or 90 degree to the surface of the mass. So if you have done that past year question with the random meteorite one, it's the same idea. Okay, this field must always be 90 degree to the center of the mass, and if the mass is a perfect sphere or almost perfect sphere, then we will call this a radial field. Similar to point charges, there's another similarity would be it has kind of like the same shape, also radial field. And if it's a charged sphere, this will be 90 degree to the surface of the charged conductor. But what are the differences between the gravitational field on the left and the electric fields on the right? You will notice that for electric fields, there are two diagrams, and there's a reason why there are two diagrams because one arrows are pointing outwards and the other one, the pair arrows, is pointing inwards. Whereas for gravitational field, the arrows are always pointing inwards. Now, why is that? Well, if we think about it right, gravity is only attractive. That's why you see the direction of the arrow is only pointing inwards here. Because gravity is always attractive. Whereas for this one, gravity, it can be repulsive, it can be attractive, because the charge that we are using as a test charge is a positive test charge. So the direction of the arrow shows you the direction of force on the charge. So let's say you have a point mass, okay, somewhere lah, maybe there's a meteorite falling towards the earth and the world is ending. Joking, joking. So you can notice that the W, which is known as weight or gravitational force, is always kind of directed following the direction of the arrow. See, I draw many, many W's. They are all directed towards the center. Whereas for your radial field, this is the force acting on a positive charge. So if let's say you have a positive charge here, like so, like down here, okay, this positive charge will experience a repulsive force like this one, so same direction, okay. And if let's say the positive charge is here, it will experience an attractive force like so. So you can see that we are taking the positive charge as your test charge, and hence the lines are drawn that way. Okay, so hopefully that's clear, and you have covered this in AS actually. So when we drew it this way, right, you will notice that it can be sometimes attractive and sometimes repulsive. So now we are going to move on based on the field lines that we've drawn to talk about what are the nature of the forces of the gravitational field and the electric field. So I think when you think about nature of forces, right, the first one that we have already covered is that this one is always attractive. So gravity is always attractive. If you find a gravitational force that's repulsive and it's not an antimatter, let me know. We can go win some Nobel Prizes. Okay. For point charges or electric force, it can be either attractive or repulsive, depending on context, okay, depending on the situation, the charge distribution, the polarity, okay. And the gravitational force is proportional to the product of their masses. Electric force is proportional to the product of their charges. Okay, so I'm just going to write out the equation to remind ourselves. Your gravitational force Fg is G m1 m2 over r squared. So let's say you have a mass m1 and you have a mass m2 and they are attracted to each other because gravity is always attractive and their separation is r. Okay, this is what law are? Newton's law of gravitation. Okay, similarly when we think about point charges, right? Okay, here you will have one charge, let's say call this Q1, and you have another charge Q2. Depending on the polarity of Q1 and Q2, they could attract, they could repel, we don't know. Okay, so let's say they are both positive. Okay, so this one will repel, just going to label this one as F. Just I'll label this one as F. Okay, so this is Fg and this is Fe. All right, so just a quick reminder of how Coulomb's law look like. This is R. So you can see it's as they are pretty similar, which is kind of amazing, don't you think? That something as big as the planet and something as small as an electron or a proton have similar but not the same relationships. So instead of using K, I will use 4 pi epsilon naught r square in this expression. You will see why pretty quickly. So first thing, the force for gravity is proportional to the product of their masses. So you can see the M1, M2 here. The bigger the mass, the stronger the force. And this one will be directly proportional to the product of their charges. Q1, Q2. The stronger the charge, or the larger the charge, the stronger the electric force. Okay, first one. Second one, which is similar for both, is that they are inversely proportional to the square of their separation. So this is why r square is down here. This r square is here. So inversely proportional the square of their separation. Which makes sense, right? The further these two things are, their interaction will be weaker. All right. So here is where they begin to differ, besides the attractive and repulsive part, which will be, does the magnitude of the force depend on where the force, where the object is? Like for example, will this gravitational force change if let's say I submerge planet and moon inside a liquid? Will it change? Will the gravitational attraction change if let's say the planet and the moon is not in vacuum? It's not. Okay, so this one is pretty logical, right? If not, then it's pretty scary. You solar wind blow a bit, then the gravitational forces change, then the Earth might not be in the orbit anymore. It might fly away, insufficient centripetal forces. So it's pretty great that this one is independent of medium. So this gravitational constant G is the same everywhere. It's the same in vacuum, it's the same in water, it's the same in, it doesn't depend on anything else. All right. Whereas for electric force, it is dependent on medium, which kind of makes sense, right? If you have forces between these two charged Q1 and Q2, if it's in a vacuum, then they have nothing to polarize. The field is actually quite weak. But if you put it inside, let's say, a semiconducting material, or maybe something that has a high, that can have a easy for you to form hydrogen bonding, like for example, water, then the electric force will actually be stronger because the medium matters. So this one, I'm just going to swap out the color. This is dependent on the medium because of this term epsilon naught. Okay, so if you need a refresher, right, epsilon naught is the permittivity of free space. So this one is for vacuum only. But sometimes we put inside some dielectric like ceramic. Sometimes we will use some liquid. So different material. will have different epsilon. Okay, so epsilon, I mean, it's called the relative permittivity lah. It's not really in the A-level syllabus, but this one, epsilon r, this one will depend on the medium. Okay, so meaning this epsilon naught can change one, but in your syllabus, we always assume that the charges are in vacuum, which is great. All right, and this one, just a reminder again, this G, independent of medium G, G is constant. It's a bit like the speed of light, all the universal constant, it will not change unless you broke science. Okay, so directly, I mean, inversely proportional to separation, and one is independent and one is dependent on medium. Next, both forces are very weak. Huh? Means very weak? Yes, but gravity, sun, moon, dude. The gravitational force between you and your laptop or whatever screen you're viewing right now is negligible because this constant G is pretty small. Remember? So this is actually a weak force. It's very weak. And also at the same time, not just weak, it is also long range. Long range here means what? Meaning I don't have to be very close for force to act. Where is the sun? The sun is 8 light minutes away. Basically, the sun is very, 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 very far away. But thank goodness, it is still able to attract the Earth so the Earth can orbit in its nice circular orbit. Okay? I mean, think about it. If, let's say, gravity is short range, then GGO, who is going to provide the necessary centripetal force for Earth to move in its own orbit? Yep. So this one has to be weak, but long range. Electric force is also very weak thanks to the epsilon naught. Epsilon naught is pretty small. I mean, in this case, epsilon naught is pretty big. Okay, so your K, remember the K here, the constants makes this force quite weak. I mean, it is slightly stronger than gravity, but apples and oranges, you can't really compare them that way. Okay, which one is stronger? Magnet. Okay, so one is long range. Just think of Earth lah. Who provides the centripetal force for Earth to move in its orbit? The sun. And the sun is far, far away. Okay, this one is short range. Example of short range is, for example, let's say you do the classic electrostatic demonstration where you take a plastic ruler. Okay, let me get my plastic ruler. And get a plastic ruler, and then you go wipe it. And then when you wipe it, you put it near your hair, and then you see it attract your hair. Does it also attract someone else's hair that's sitting beside you? No. Does it attract the hair at the back of your head? No. So the electrostatic force is very weak and also very short range. Okay, so that is the next comparison. Okay, and the following one would be, as I've drawn earlier before, the forces has to be parallel to the field lines. Okay, are there any forces that are not parallel? Yes, magnetic force. Think of your Fleming's left-hand rule. Okay, so that one we'll compare later since you have not studied magnetic force yet. Okay, and this too is independent of the state of motion. Okay, what I mean by that is, let's think about gravity. You're sitting on a chair. Your gravitational force is mg. You are sitting in the car and the car is moving horizontally. Gravitational force is also mg. You decided to jump off a table. Your gravitational force is still mg. You're on an aeroplane and the aeroplane is flying in a curve. Gravitational force is mg. You're on a bank curve moving in a circle. Gravitational force is mg. So it doesn't really matter how you move. Gravitational force is mg lah. The effect of the mg is a totally different story. Whether it causes your apparent weight to increase, let's say you're in the lift, whether it provides centripetal force, and for a moment you don't feel the gravity. So all this is dependent on how you move, but the actual gravity that's acting on you is the same. It doesn't matter whether you're moving to the left, to the right, up, down, whichever direction. Same goes for electric force. Okay. So I think a good example for me to show you that is actually to draw out certain diagrams that you have seen before. So in this case, right, we know that the gravitational field exists due to mass. If there's no mass, you cannot interact with the gravitational field. For example, light. based on our understanding right now in your syllabus, light does not interact with gravity. For now, until Einstein came in. Okay, then after that, it follows the inverse square law. Okay, so this is the nature of the field strength. Whereas um, electric force exists due to charges. So for you to set up an electric field, you need charge. And this one follows the inverse square law. Okay, they would following the inverse square law. So if in case you kind of need a bit help to remember gravi- gravitational the gravitational force equation, the gravitational force or the gravitational field strength equation, lowercase g, is gm over r squared. Okay, just like the electric field strength, E is equal to kq over r squared. So this is where the inverse square law come in. Okay, and this is where the charge and the mass comes in. So if you remember something very similar, let's say you have a table, okay, and then remember the good old days where you have a ball rolling off a table, you know, and when the ball rolls off a table, let's say it has an initial speed here of u, this ball will follow a parabola, right? And then it will fall to the ground. So this thing, this is a parabolic path. All right. If you want to draw the direction of force, your mg is always pointing downwards. Don't care where you are, see? Independent of the vector velocity. So this one will be mg, mg, mg. You can see the weight is always pointing downwards, okay, towards the center of the earth. Means electric field got similar. Oh, remember we have the parallel plate, and parallel plate. And let's say I make this plate negative lah. Connect to a power supply like this. The other plate is positive. Then I allow a positive charge to come in. So of course, if the positive charge enters this with a speed u, it will begin to be attracted towards the negative plate. This is also a parabolic path. And where's the direction of the electric force? Well, again, your Fe is always in the same direction. Okay, so this is your Fe. And Fe has to be parallel to the electric field line. These are all AS stuff. Okay, so it's parabola. This is a parabola. Okay, magnetic field is not a parabola. So magnetic field is the odd one out lah. You stay tuned very soon. Okay, so when we say it exists due to mass, right, and it doesn't follow the state of motion, this is what we meant. Doesn't matter where, because you can see the direction of V keeps changing, but the direction of Fe is the same. Okay, we are comparing it this way later, it will make more sense, especially when we have talked about magnetic fields. All right, so let's move on to the final one. Gravitational potential. Now this one is their favorite thing to ask. This one. I'm just gonna put a star here. Wow, very important. Okay, because if you've done enough chapter 8 gravitational field question, they always ask you, why is the gravitational field negative? Why is the gravitational potential negative? Gravitational potential is negative because gravitational field is always attractive, and since the gravitational potential at infinity is zero, work is always done by the gravitational field to bring it from infinity to a point. Okay, go review your notes. But this is always attractive. So, your gravitational potential, given the symbol psi, is gm over r. But don't forget, negative. Okay, negative gm over r. All right, and for our electric potential, V, it can be positive or negative depending on the charge polarity. Okay, but both will follow inverse law because of the 1 over r. So V is proportional to 1 over r, and then the other one, the gravitational potential, is proportional to 1 over r. Okay, so here you will notice that potential is actually, although it's very counterintuitive, hopefully all the nice potential diagrams that we have drawn for you, remember this one, actually helps you decide what is the acceleration and how does the point charge travel inside different fields lah. So go watch that video. Okay, because the potential helps us decide the motion of particles inside the field. So yeah, so in this video, we compared the gravitational and the electric field. I tease you a bit about the magnetic field here and there. If you know the magnetic field from your IG study or your SPM studies or your previous studies, I would suggest you think about how is magnetic field different than these two. Okay, so we will cover the last part when we talk about magnetic fields. We have looked at the field patterns. All right, we have extensively examine their differences. So your past year question, they may ask you to write one or two differences. Sometimes they will cheat you a bit lah. They will tell you one of the differences inside the question, and then they say, besides this difference, compare the fields. Then you make sure you don't write the thing that they already written wrong. Okay. So here we then compare the nature of the field strength. One is dependent on mass, one is dependent on charge. And the important thing is that Fe and Fg is always in the same direction. Doesn't depend on how the particle is moving. Okay, and finally the nature of potential, which helps us decide whether the particle is moving faster and faster or slower and slower, and who is doing the work. All right, so I think that's it for this question. Please go do some past years. Take care of yourself. Like and subscribe if you find this helpful. Share it with your friends. I will see you in the next video. Bye bye.